Welcome to today's webinar entitled The Performance of Streetscape Bioretention Systems in South East Queensland. Presenting this webinar, we will have Lucy Peljo, the Senior Environmental Scientist at BMT-WBM, and Brad Dalrymple, the Principal Environmental Engineer also at BMT-WBM. Before we get started, I'll go over a few items so you know how to participate in this webinar. If you have any questions or any relevant questions, you can click on the right and you will see a question panel. Just type your question into that question panel, and time permitting, Lucy and Brad will answer all your questions. You can send these questions at any time and they will be addressed at the end of the webinar during the Q&A session. Thank you very much, and now I would like to hand the webinar over to Lucy and Brad.
Hi everyone. Feels a bit strange actually sitting here talking and not getting a response, but anyway, we're talking about bioretention systems. So what do we know about bioretention systems? There's been a lot of research into bioretention systems over the years with lab studies, including work undertaken by the Facility for Advancing Water Biofiltration, or FORB, Griffith University, Monash University, and many others. These studies have investigated questions about vegetation species like which plant species will support the best long-term removal of pollutants, questions about filter media like what is the optimal filter media type, how does the filter media perform over time, is there clogging, and questions about the design of the systems like how does a submerged zone benefit the pollutant removal and what's the optimal filter media depth. These studies have provided us with a great wealth of knowledge and provide the benefit of trialling the systems in controlled environments. However, the field-based studies are few and far between, particularly in South East Queensland. So there have been some field studies. Terry Luck and Peter Nichols undertook a study on a 10-year-old system in an industrial estate in Caloundra. They used simulated rainfall events and used synthetic stormwater to dose 3 bioretention basins and measured the pollutant concentrations and flow volumes. In their study, they found an average volumetric reduction of their systems of around 62%. Alastair Mackenzie McCarg, Nick Smith and Belinda Hatt undertook a similar study in Brisbane, analysing stormwater treatment performance of 2 streetscape bioretention systems. A rainfall event of approximately a 3-month ARI. In their study, they found the volumetric reduction was between 14 and 30%, or an average of 23%. In 2010, Nat Parker undertook research at a bioretention basin at Coomera Waters in Queensland. Nat monitored the inflow and outflow of real rainfall events and found that of the 18 events when bypass did not occur, volumetric reduction was on average 42%. The 4th study was undertaken in Melbourne by Belinda Hatt, Tim Fletcher and Anna Delatic in 2009 of a lined bioretention basin in a car park area. They found that of the 17 events that did not bypass the system, on average 33% of the inflow volume was retained by the bioretention basin, with a range of between 15 and 83%. So we have lots of lab experiments that have provided a huge amount of information to develop guidelines. And we have several field-based studies, some of which have been undertaken in South East Queensland. But how does this relate to our site at the Sunshine Coast in Queensland, where we have a high-value ecosystem downstream to protect? How are we going to start answering this question? For this, we undertook some site-specific field-based monitoring at the Sunshine Coast in Queensland. Specifically, we wanted to ensure the systems work well, as well in the real world, for local conditions as predicted by music. We also wanted to use the learnings gained to potentially optimise the design, construction and establishment of the systems to maximise the performance and function of bioretention systems. The study site is at Caloundra on the Sunshine Coast, which is about a 1-hour drive north of Brisbane. We looked at several sites in the area and we based our sites on a range of criteria, including the operational life or time in the ground. All of the sites we selected had been constructed for at least 2 years. The outlet configuration, which we needed to easily access and monitor the outflow. Safety was an important consideration because we will be monitoring in sites next to the road, so we needed to create a barrier and preferred quieter streets. Finally, we selected small systems so that the volume required to evaluate the systems was limited to ensure ease of undertaking the experiment. The final 4 sites we selected were all located in Bells Reach, Caloundra, which you can see on this slide. A summary of the bioretention system properties is shown in this slide. The bioretention properties were all standard and depths were within specified guidelines. The planting schedule was 50% carex and 50% knobby clubrush. And carex is a plant that's known to perform well and keep the filter porous and enhance nitrogen removal of the system. The methodology utilised for our experiment was based on methods developed by Belinda Hatt when she was at FORB. It involved the simulation of a rain event and the addition of a predetermined volume of semi-synthetic stormwater to the system. The semi-synthetic stormwater was created with sediment from an existing stormwater wetland and dosed with chemicals to match typical stormwater pollutant concentrations. Sediment was collected from the Cressy Street wetland in Wavell Heights, Brisbane. The sediment collected was analysed and additional chemicals were added to match target pollutant concentrations that are typical for South East Queensland. The target pollutants were similar to those used in a previous study undertaken in Brisbane. The runoff volumes were based on the capacity of each system to hold water, which we estimated prior to the experiments. If we did some calculations afterwards, and if we assume the bioretention systems are 1% of a fully impervious catchment area, this would be equivalent to a rainfall depth across the catchment of approximately 4 to 5 millimetres. The experiments were undertaken on the 4th and 5th of June 2015. And in the 2 weeks leading up to the sampling, there had been no rain. However, we did a trial at Site A 1 week prior to the experiment, and at the same time, Site B and Site C also received some dechlorinated water. These photos show the 4 main steps during the experiment. In the top left, Jack is adding a chemical which dechlorinates the water. Then in the top right picture, you can see Brad adding pollutants. The stormwater is then discharged, and you can see that in the bottom left. And in the bottom right, Daniel is measuring the flow and collecting samples. Now, we did have a video to show you, and unfortunately, due to quality issues, sorry, we can't show it, but after this presentation, we will direct you to a YouTube site where you can have a look at the video of the experiment. There's the video. So onto some results. The hydrographs of the inflow and under drainage outflow for each bioretention basin are shown. As you can see, there was a significant slowing of flows from the inflow to the outflow. Timing of the peak flows also was significantly attenuated. The peak outflow occurred approximately 50 minutes after the commencement of inflow into the systems. An outflow occurred over a much longer period. This figure highlights the volume of flow reduction between the inflow and outflow. This is probably one of the most interesting things that we found. So you can see site A, we put in 2,000 litres and it was reduced by approximately 1,400 litres. Site B, there was a reduction of 1,600 litres. Site C, it went from 3,000 down to 840. And site D, there was a reduction of approximately 2,600 litres. So that was a lot in site D. As I mentioned earlier, we did undertake a trial on site A 1 week prior to the experiment, with some water also being dosed into site B and C, which could be the reason why there was no, why the reduction in volume in site D is much greater. And you can see here the average flow reduction across all 4 sites. There was on average 67%, and it ranged between 39% at site B to 87% at site D. So I'm just going to pass over to Brad to talk about a bit more about the flow reduction results.
Yeah. Good afternoon, everyone. This is Brad Dalrymple here. Yeah, look, this is one of the really interesting aspects of the study. Like, I guess particularly as stormwater quality engineers and music modelers, there's a real focus on water quality. But in my mind, the flow attenuation and flow reduction provided by these bioretention systems is as important, if not more important, than water quality. And the results that other people have shown, which Lucy talked about at the start of the presentation, show similar results to what we found as well, like the Terry Lukey study and Alice Mackenzie McCargan, Nat Parker's, Belinda Hatz, etc. They all show significant flow reduction volumes, even in systems that are apparently lined. And often surrounded by clay soils. So the water is being lost where it goes, whether it be evapotranspired or exfiltrated, or just sort of sitting in the underneath the under drainage, for example. We're not entirely sure, but we are seeing significant reductions in flow volumes, and that's what other people have also shown, and we are seeing significant reductions in flow volumes. You can see Terry Lukey's study, for example, 62% on average flow reduction. Alice Mackenzie McCarg showed on average 23%, and Belinda Hatz, and particularly Belinda Hatz, they looked at real events in a lined system, and they showed essentially a third of all flows are just being lost from the system. And from a waterway health perspective, that's really important. So reducing the frequency and volume of those flows is really important to the health of our waterways. But if you go to the next slide, Lucy, how does that compare to what music shows? So as an example, we took just a typical 1 hectare urban residential source node in music, modeled it with had a typically sized bioretention basin downstream, standard parameters in accordance with the guidelines, and we used Caloundra rainfall and potential evapotranspiration data. Modeled at 6-minute time steps over a 10-year period, again, all in accordance with the guidelines. Now, so that's our music model. So what does music predict for this little example site? So this is actually just the results of the music model, showing the node water balance on the top and the just the mean annual loads across the bioretention basin at the bottom. Interestingly, you see the music predicts a 1.8% reduction in flow volume across the bioretention system. Now, again, this is a system, typical bioretention basin modeled with 0 exfiltration in accordance with the guidelines, and we're only showing 2% flow reduction. Now, that is obviously significantly lower than what is being predicted, what is being observed in our study, but also what has been previously observed in other studies around Australia as well. And we haven't shown other studies from overseas, but it more or less show similar results, against high reductions in flow volume. If you look at a bit closer in the music model, so the next slide shows this is a time series graph looking at the bioretention node at 6-minute time steps. So you can see the red lines show flow into the bioretention system, and the blue lines show flow out. And you can see at a small time step, there's a little bit of a difference between the red line and the blue line. So there's essentially a little bit of flow attenuation, flow slowing across the bioretention basin, but that water does come out. And if you look at the same results at a daily time step, so again, this is that across the same bioretention node, same model, but looking at the inflow versus the outflow at a daily time step, you can see there's essentially no difference at all between the inflow and the outflow. So what comes in is what's going out. So again, consistent with what we saw before, showing essentially very little flow volume reduction across the bioretention system as modeled in music. Now, is that appropriate? Before we might actually save that discussion a little bit later on, but I'll let Lucy talk about water quality as well.
Okay, so here's some water quality results for the pollutant concentration reduction. You can see that there was a fairly large pollutant concentration reduction occurring through the bioretention system, with total suspended solids reduced by, on average, 91%. Total TP concentrations reduced by 83% on average. Orthophosphorus, 20%. And orthophosphorus is important to manage as it's strongly correlated with algal growth in waterways. TN concentrations were reduced by 33%. And with the exception of ammonia, all dissolved species of nitrogen were typically more difficult to reduce. This is important because these are the more bioavailable and important species of nutrients with respect to receiving waterways. You can see nitrate and nitrite showed the least reduction in concentration, which I'll show in the next slide, and pretty significant reductions you can see as well in metal concentrations, with all metals reduced by more than 90%. So interestingly, you can see the reductions for nitrate and nitrite. And what's interesting is outflow concentration is higher than the inflow at site D. So the increase in concentration or leaching of NOx from site D can have important consequences for bioretention design at the site. Research by Zinger and others has shown that including a saturated zone, the accumulation of nitrate in the filter media can be delayed. The inclusion of a saturated zone can also buffer the plant and microbial community from variations in soil moisture content. So site D was the only site that didn't receive any water in that 2 weeks prior to the experiment. So moving on to pollutant load reduction results, as we saw, the flow reductions were significant, and the concentrations, which is what we're seeing here, is a combination of those two. A large proportion of this reduction would be a result of the reduction in flow between the inlet and bioretention drainage. The other thing although I've put on here the water quality objectives for South East Queensland, and you can see that all of the TSS, TN and TP results look great. It's also important to take note that our experiment only monitored what went through the system and doesn't incorporate anything that bypasses and therefore receives no treatment. So in summary, we monitored 4 streetscape bioretention systems in South East Queensland, and the results showed an average reduction in flow volume of 67% with a range of between 39 and 87%. Pollutant concentration reductions were greater than 80% for total suspended solids, total phosphorus and heavy metals, but they were a bit more variable for the dissolved nutrients. And the pollutant load reductions were very high as a result of the flow reduction and pollutant concentration reduction. Now just pass back to Brad to where to from here.
Yeah, look, thanks, Lucy. So this work was done for a client of ours who has a real interest in making sure that these systems work properly, but also they have a real interest in making sure that they are optimizing the design and performance of these systems moving forward as well. So there's a number of things that we're doing in terms of monitoring and also trialing different configurations. So this is just one study we're doing. It's a very, I'd call it a very preliminary study. We did only look at small flow events. We did only look at 4 systems. Really a snapshot in time, and whilst they've been operating for a few years, they still are relatively young systems, but we are doing a whole bunch of stuff up in Caloundra. So one thing we're doing, which is really interesting, we're actually trialing different configurations of bioretention systems. So there's essentially about 18 different types of configurations being trialed in a fairly small area in Caloundra, looking at different filter media types. So that includes particularly different amounts of organic material and adding in stuff like zeolite, perlite, etc. Trialing a few different under drainage configurations, including saturated zones and the like, and also different vegetation types, the full gamut of species, instead of just using the same palette of species that probably everyone seems to use nowadays. We're really trialing a different range of species. And we're going to look at a whole bunch of things. Looking at, whilst give these systems a few years to establish, we're going to look at how effective they are at removing pollution. So whether it be real events or synthetic storm events like we did for this experiment. We're also very interested to see how different systems just look and function. Is vegetation growth better in organic material, sorry, systems with a high organic material, for example, or are they maintaining better porosity or whatever? So looking at a bunch of factors like that, and with the key aim of making sure that these systems are actually working as good or better than what music is predicting, but also making sure that we take whatever knowledge we gain through these experiments and trials and use them in future systems, not just within Caloundra, but for other projects as well. And obviously, sharing this information and knowledge. So again, it's just probably the first experiment and trial of an extensive amount of investigation we're looking to do in relation to the performance of different stormwater treatment devices. So that's it. I think we're up to. We've had a few questions come in. If you do have questions that you'd like us to answer, I know you guys can actually post them to the webinar. There's a fair few that have come through already, so what we might do is try and go from top to finish and try our best to answer those questions. If we can't answer some of them, we'll obviously have to take a few of them on notice. But I know Mark Gibson is an avid listener, and I see a fair few from Lachlan as well. So one of Mark's questions, and a couple other people have asked us as well, were whether any of the types of line, and also I think some people asked whether saturated zones as well. They were all unlined systems, and they were all conventional under drainage systems, so no saturated zone at all. So I guess water coming into the system would either drain through the under drainage or potentially seep out the bottom or out the sides. Yeah. So, and Mark's made a comment in relation to that, saying, water losses must be via the stone layers surrounding the drainage pipes and transition layer. Yeah, possibly.
Oh, that may be me.
Yeah, sorry. We're just going to make sure that when Lucy sits near me, she shouldn't have a speaker. So it may be best if you keep that off. Sorry if you've heard a bit of echo in the background there. I'll scroll through to some other. One of the questions that Lachlan has asked, and it might be best if Lucy answers this one, is how dry were the systems beforehand, and what kind of storage was available? Were we able to estimate this?
So we haven't estimated the storage, but the systems I mentioned felt like Site D was dry. Site A, B, and C had all received water in the exactly 1 week prior to the experiment. So A, B, and C weren't as dry as Site D, which was possibly why we saw a greater volume reduction at Site D.
But when you say wet, when you say they were wetted, there was a lot of volume going into these systems in the week prior, wasn't there? Like we more or less saturated them, or at least one of them?
Yeah.
Yeah.
Yeah, Site A definitely saturated.
Yeah.
Site B and C both received some volume of water.
So that's one thing. So I guess the dryness was a little bit variable. One system was fully saturated, like completely filled up to the brink, to the overflow width with water. Another two were slightly watered, I guess you'd say. Another one was could have been completely dry. One question from Brian was, Brian Corrigan, is, do we have any information on the impacts of larger events? Is the high reduction a result of no bypass type flows, where music is modelling all flows? Potentially. So yeah, we did focus only on, I guess, what you consider small events. So we filled up the systems essentially to the overflow spillway we're in these bioretention systems. So yeah, some amounts of the, I guess, potentially higher losses observed would be due to the fact that we looked at smaller events with no bypass. But having said that, the majority of flows entering a bioretention system, provided suitably sized, should still be being retained and seeping through the filter media. Only a small portion would actually overflow the spillway weir. Yeah, we've answered that one. So here we go. I'm just reading these questions out loud. Yeah. Yeah, Lachlan asked a good question. Do you think, I'll read it out here, do you think it would be possible to have a guideline that was just volumetric based rather than TSS, TP and TN load based, particularly given the importance of managing flow volumes to achieve some receiving water objectives? I think what also Lachlan means is, would it be possible to have like an appropriate objective? Like dare I say, a frequent flow management objective or something similar to that? Like, should we be actually, instead of just targeting 45% TN and 80% TP and 60% TS, whatever it is, should we have a flow reduction target? I absolutely think we should. But my only concern in relation to that is actually whether music is actually appropriately modelling the hydrologic performance of bioretention systems. What I would say is, whilst music is a fantastic tool, and I better say that because eWater are listening. No, I'm being honest, but music is definitely the best tool we have available in relation to predicting the performance of different devices, etc. But I do think some attention should be given to reviewing how music is modelling the performance of bioretention systems in terms of the hydrologic performance. And one thing I'd also suggest is it, and in relation to the music modelling guideline, which currently says that we should assume zero exfiltration when modelling treatment devices when demonstrating compliance with the pollutant load reduction targets, is that really means that we are really focusing specifically on water quality, whereas I think we probably should be giving far more attention and putting far more importance on hydrologic objectives. So I definitely think Lachlan is on the money there. Lucy, do you agree? Totally, she says. I see one from Andy Hornbuckle. Hello, Andy. So the load, I'll quote Andy, the load and flow reductions appear high for these 4 to 5 millimetre equivalent events. But on an annual basis, wouldn't this be a small percentage of annual rainfall volume? I think we are obviously small rainfall events, small and frequent rainfall events are, I guess, only a portion of the overall flow volume, but they still are a significant portion of the flow volume. And I think particularly in relation to protecting the health of our waterways, I think the small frequent flow events are probably more important than the larger events that would typically bypass a typical treatment device. So the old rule of thumb is, what is it? 90% of flows are up to the Q3 month peak flow rate. So if we can get flows up to that volume, which is what I think Alistair Mackenzie McCarg and Terry Lukey and all those guys, they did simulate those events up to those volumes, but they still are predicting significant flow reductions. So yeah, look, I think whilst we are showing percentage reductions for our events, yeah, by all means, we would expect lower reductions if we looked at the whole gamut of flow events. I hope that answers your question, Andy, but you can give me a shout on the phone later if we haven't. I'm just, oh, geez. I might have to, it's one from Dale. Yeah, Dale Brown asked a good question. I'll quote Dale: since you know the systems are unlined and that there will be infiltration, have you tried modelling them in music, allowing for an estimated infiltration based on soils? No, we haven't. We didn't really have any significant knowledge in relation to the in situ permeability of the soils, so we couldn't do that, but it's certainly something we could do. And this is, like I mentioned before, it's still a fairly preliminary investigation. There's a whole bunch of things that, you know, stormwater and music nerds like me and you, Dale, could go to town on, but it is just an initial investigation. But having said that, the results are fairly consistent with what we've seen in other systems. And also, it's just important to note that we are also comparing results to systems that are lined, and even with the lines, just so what Oregon asks a result of surface tension. Yeah, look, Alan Hoban is there, as I thought he might be. He asked a good question, and this is a question that Alan has also proposed before. Apologies, I've just been notified by eWater that you might have not have heard us for a little while. We apparently lost audio for about a minute. You missed it. That were all my funny jokes. I had a minute of just crackers. But apologies for that, but we are back. But Alan Hoban asked the question, and I have heard him ask his question before recently. I'll quote, what does this mean for local authorities when assessing stormwater management plans, where music models are prepared in conformance with current guidelines? Excellent question. I honestly think we, as an industry, need to, I'm guessing this is in relation to the volume reduction and the fact that we are currently saying that you have to assume no exfiltration, and music is predicting very little loss across bioretention systems. It's a really good question, and to be honest, I don't really know the specific answer. I'm not sure if Lucy can chime in, but I just think with any model, and recognizing that music is probably the best model we have available, but it is still a model, and I think it should be used with an element of caution. And I think particularly when we are looking at vegetative systems like bioretention systems, I think it's reasonable to believe that the model may not be accurately predicting the performance of these systems, particularly in relation to hydrologic performance. So I think like music, like any model, should be used with a degree of caution. Having said that, I still think the targets that we have available, they're not based on what is needed to protect the waterways. It's what is currently considered reasonable and practical outcomes in terms of stormwater quality and devices. So a bioretention system sized in accordance with the guidelines to meet the SPP target seems to be a reasonable and practical strategy. And sort of revised objectives, I think that's a reasonable line in the sand to take. Having said that, I still think this topic of the hydrologic performance of treatment devices definitely needs more attention, and it definitely should be investigated further by our industry, with the e-water guys paying close attention to the results. We're getting a lot of thank yous. I'm going to skip through some of those. So one from Andy Hornbuckle. There might be another question I have to take on notice, but I'll see how we go. How do you suggest this is Andy. How do you suggest we address, in brackets with design, the issue of the significant nutrient export in the context that this is a very small event being sampled, and how much export do you think would happen in larger events? That's a great question, Andy. I think we probably have talked about it a little bit, but again, it is just a preliminary investigation. I might have to take that on notice because we've got a fair few others. Answer that appropriately. So this is one from Jason Fan. Sorry, I can't pronounce your last name. So the question is, were the filter media properties recorded for each side? And if so, how did it compare to the 4 prescribed values modeled in music? Yeah, I personally, well, Lucy can't recall, but I'm pretty confident that we did do the soil samples to check to see what the properties were like, but also the devices were reasonably constructed, and we got as constructed design drawings, and I'm quite confident the filter media specifications were available in those, and they would have definitely been in accordance with the 4 guidelines. But yeah, certainly we can check that as well. So I'm just trying to think, was there another question we skipped? Which one? Oh yeah, this was a question from, now this is probably our last question, but if you've got further questions, feel free to swing them through now, because we'll try and answer them. So this is a question from Sayamsul Hidayat. Apologies if I've mispronounced that. So the question is, in developing countries, attention given to urban runoff quality may not be as high as that in developed countries. As a result, little to none record on historic water quality can be found. Based on your experience, what is the most important parameter / pollutant to be modeled in developing countries? I think I don't want to group developing countries all in the one basket, but certainly if you just look at Asia, for example, like how that's a significant that's a major source of pollutants, litter in our waterways, in our oceans. I would have thought that'd be a really good place to start. Just the amount of litter or gross pollutants that is being generated. I think if developing countries can do something towards mitigating the gross pollutant loads coming from their catchments, that would be a great place to start. And to be honest, it's probably where Australia started back in the day as well. We focused on gross pollutants because they were the most visible pollutant that got the most, I guess, community complaints. And since we've sort of gone some way in mitigating those pollutant loads, whilst there's a lot of work still to be done, that has been given a lot of attention, and we have built our own capacity internally in relation to stormwater management and moved on to other pollutants as well, such as total suspended solids and nutrients and etc. I'll just make sure. Thank you, everybody. That's the last of our questions. Would just personally like to thank everyone for tuning in. We've had a great turnout. I think we've had about 78 people dial in. You guys have asked some great questions, and you've given us some lovely things, lovely compliments on the messenger board as well, which is very nice. But yeah, certainly thanks very much for tuning in. Thank you, Lucy, for doing such a great job on the presentation. She's an absolute star. I don't want to take any credit. This has been Lucy's baby, and also, thank you very much for Bioretention for hosting us today. It's been really appreciated. And if you'd like to contact us or ask any questions, just obviously both me and Lucy work at BMT. You can give us a call or drop whatever you like to do. Happy to chat anytime. So thank you.
Yeah, thank you very much, Brad and Lucy. That was a great presentation. I thoroughly enjoyed it.
Thank you, Miha.
Yes, in relation to the content, we are obviously paying great attention to what the industry is doing, and we're looking forward to research, to hardcore research, performed by people like you guys and universities. And absolutely, the moment the science is in, it's absolutely the moment when we're going to incorporate it into music and make it better. Now, again, thank you very much, and thank you all of you guys who dialed in and took time out of your work schedule to be here with us and to listen to this cool presentation. And if you have any questions about music, obviously you can email me. Most of you know my email, or you can just email support@iwara.org.au. We're definitely going to look at that and address your questions. I will be sending out a follow-up email with the link to the webinar recording, so you guys can view it again, or you can share it with your colleagues if you wish to. Most certainly, please give us feedback if you have any feedback about the webinar or ideas what we can look at in the future. More than happy to look at that as well. And on behalf of iWara and our team here and our presenters, again, thanks for joining, and we'll see you at the next webinar.